Hello, good morning everyone. Today we will be presenting our study on integration on renewable energy sources with a focus on circuit breaker coordination and fault analysis using ETAP software. For the introduction, in modern power networks, the transition toward renewable energy, especially wind energy, plays a crucial role in building a sustainable future. However, this shift introduces new protection challenges. Traditional power systems were originally designed for unidirectional power flow, where energy flows from centralized power stations to consumers. But with wind and other distributed energy sources connected at various points in the network, we now face bidirectional power flow. This change causes protection devices to behave unpredictably. For instance, relays may miscoordinate or fault currents may appear lower or behave differently. This undermines system reliability. Here, circuit breakers plays a key role. They are designed to detect and isolate faults quickly. However, in renewable-based networks, coordinating them properly with protection relays is more complex. To overcome this, the use of adaptive protection schemes becomes essential. These are flexible systems that can respond in real time to change in load, direction of current, and fault behavior. Make sure to ensuring both safety and stability. For the problem statement, first, we integrating renewable systems like wind generators introduces protection and coordination challenges, especially under fault conditions. Traditional grids aren't built to handle the dynamic and variable behavior of renewable energy. This includes changes in fault current magnitude, voltage fluctuations, and unpredictable power directions. Without an updated and reliable protection scheme, faults can spread across the network, risking equipment damage, longer downtime, and even widespread outages. That is why accurate circuit breaker operation is so critical. We need to ensure that when a fault happens, the breaker quickly isolates the faulty bus while leaving the rest of the system unaffected. Our system operates across multiple voltage levels: 110 kV, 33 kV, and 11 kV. This complexity makes the coordination between relays and circuit breakers even more challenging. And finally, manual methods or visual observations on single-line diagrams are no longer sufficient. We need real-time simulations tools like ETAP to test, analyze, and verify the protection behavior under different fault scenarios.
So we start with flowchart. First, research and system selection. Start by finding relevant reference paper on wind generator system. By using ETAP software, select or configure your wind generator system based on the research. If the system isn't suitable, revisit the research. Second, circuit design and protection. Design the electrical circuit in ETAP software, following the specification from your chosen reference paper. Integrate essential protection system components such as circuit breakers into the design. Third, component parameterization. Assign appropriate electrical values like voltage, current, and impedance to every component within your design circuit. 4. Simulation and fault analysis. We need to run the simulation in ETAP software to observe the circuit's performance. Specifically, check if the value at a particular bus drops to 0 after a simulated fault. If not, refine the simulation parameters and rerun. Last, discussion of finding. Once the desired fault behavior is observed, thoroughly analyze the simulation result. So let's start looking at the power grid characteristic we are using in our analysis. This slide shows the key parameter for our power grid, specifically a 110 kV system operating in a swing mode. First, for power grid. Power grid is act as the primary source maintaining voltage and frequency for the simulation. As we can see on the left side, under power grid rating, you can see the general operating conditions. We have set the rated kilovolt at 110 kilovolt for a balanced system. Now, we're moving to the right for power grid short circuit parameter. These values are crucial for understanding how the grid behaves under fault condition. We have specified the short circuit rating in MVA as for both three-phase and single-phase fault. Then we move on to the bus load. For the bus 1 until 3, moving on to the connection points in our system known as buses. This slide illustrates the setting for our different bus configuration. As we can see on the left, we see the parameter for bus 1, and similarly with bus 2 and bus 3, which are not shown but follow the same structure. These buses are designated with a nominal voltage of 110 kV, aligning with our main power grid connection. So we continue with bus 4 and 5. The right side of the slide shows the setting for bus 4 and bus 5. These buses represent a different voltage level, specifically 33 kV, indicating a step down or different level, different part of the network. Both sets of bus configuration include initial voltage and angle setting, and importantly, they have load diversity, factor limits and voltage limit defined, which are crucial for assessing system performance and stability under varying load conditions. Then we move to the bus 6. Continuing our discussion on the system bus configuration, this slide focuses specifically on bus 6. We can see that bus 6 is set with nominal voltage of 11 kV. This indicates another step down or a different voltage level within other buses. Now, we continue to the transformer in our system, which are crucial for changing voltage levels. As we can see on the left, we have winding transformer 1. This is significant unit with a rating of 25 MV, and it steps down to the voltage from 110 kV to 33 kV. We can see the detailed impedance values for both positive and zero sequences, which are essential for accurate fault calculation. The SR ratio is consistent at 13, a common parameter for power transformer. This transformer plays a key role in connecting the high voltage power grid to the net section of our system. On the right, we can see winding transformer 2. This transformer is much smaller, rated at 1.7 MV/A, and it further steps down the voltage from 33 kV to 11 kV.
For the data and parameter for cable, we use four identical cables, which is 1A, 1B, 1C and 1D, rated at 11 kV at 50 Hz. Each is a 3-core aluminum XLPE insulated cable with a cross-sectional area of 185 mm². The positive sequence impedance is either from the library 211 ohm per kilometer R and 93.1 ohm, which is for the reactance, or calculated 212.85 ohm for the resistance and 83.02 ohm for the reactance. For the zero sequence, two sets are considered: 335.49 ohm for the resistance and 236.47 ohm for the reactance, or 217.16 ohm for the resistance and 1474.86 ohm for the reactance. The X per R ratio range around 0.44 to 0.71 depending on source. Thermal limits are also defined: a base temperature of 90 Celsius with a minimum safe operating limit of 75 Celsius. A non-magnetic shield and 100% grounding efficiency are used to ensure accurate fault current return path. These parameters are essential for accurate fault studies, load flow analysis, and protection coordination. Differences between library and calculated values must be validated based on actual application requirements. For the wind generator data and parameter, the component label WTG1 is designated as the wind generator by the software itself. This represents the point where the wind energy conversion system connects to the main electrical grid. The rating provided in this slide is based on the industry standards and can be further developed.
The short circuit analysis was carried out on the wind generator system while it operates at its rated grid voltage of 100 kV, with the fault introduced at bus 4 to evaluate the protection response of the system during fault conditions. So this type of analysis easily shows how the fault will be isolated by the circuit breaker, and it is crucial in assessing the system's ability to withstand and recover from such disturbances. Circuit breakers are able to rapidly detect the high fault current, disconnect the faulty section, and prevent the fault from propagating further into the system. This not only safeguards the equipment from potential damage, but also minimizes the downtime and enhances the reliability of the power delivery. Furthermore, this analysis of the integration protection system in renewable energy system helps to ensure the system is able to function normally even with the fault occurrence. So figure below shows the simulation done in ETAP software for a wind generator system incorporating circuit breaker in the protection system. So in this study, the proposed 29.41 MW wind generator system includes a grid that fits into the network. With 400 MVA, the power factor becomes 0.951, which is almost close to 1, the ideal per unit value. So the value of 29.41 itself is taken from the industry, but it can be further changed according to the studies. There are additional 4 circuit breakers in the system that helps to isolate the fault wherever its location is and control the switching. The voltage used in the system is 110 kV, 33 kV and 11 kV. There are 2 capacitors located at the end of the circuit to provide reactive power support and stabilize voltage during normal operating conditions. Multiple cables are used to connect the buses. When a fault occurs at bus 4, the voltage becomes 0 kV, and this is expected at the fault point. The circuit breaker disconnected the fault at bus 4 from the rest of the healthy system. The addition of a small resistor in series with the breaker contacts will reduce the X/R ratio of the system, such that the transition offset will decay so rapidly that a zero crossing within the first cycle of fault current can be expected. Users may also choose to add small up to 0.1 second delays to trip circuits of high-speed circuit breakers to assist in the establishment of zero crossing in the fault current before attempting to interrupt it. So the need for small delays before tripping the circuit breaker may be discussed with the wind plant developer and the circuit breaker manufacturer. Since the wind turbines are often situated in remote or offshore location, this makes any repair process logistically complex and expensive. A failure in the circuit protection not only endangers equipment but also potentially disrupts regional power supply. Thus, a reliable circuit breaker is a necessity. Traditional circuit breakers are typically configured as standalone units with external grounding switches and isolators. Development in protection and switching devices are increasingly integrating internet and cloud-based technologies, thereby facilitating sophisticated remote power control and optimization from virtually any geographical point at any time. For conclusion, the detailed study and performance analysis of the integration power system protection in the renewable energy system has been studied. The system was managed to be simulated with the help of ETAP software, and detailed analysis of the short circuit simulation has been obtained. ETAP offers a vast array of modules including load flow, short circuit, arc flash, motor acceleration, harmonic transient stability, star protection and coordination, star Z protection and coordination, DC load flow, DC short circuit, DC arc flash, battery discharge and sizing, unbalanced load flow, time domain load flow, unbalanced short circuit, voltage stability, optimal power, reliability assessment, And lastly, optimal capacitor placement. The findings from this detailed simulation are crucial for validating theoretical fault current, ensuring robust and reliable integration of renewable energy sources into the existing electrical grid infrastructure.